Observe a pendulum in motion. As it swings, it carves a smooth, symmetrical arc through the air. This curve physically manifests a quadratic function. When we try to calculate the exact points where curves like this intersect a baseline, our basic algebraic tools often fail. Graphing loses precision when intersections land on endless decimals. Factoring is completely useless unless the roots happen to be clean, visible integers. To solve for exact values in every possible scenario, we rely on the quadratic formula. It is the mechanical tool designed specifically for these failures. Students are typically taught to memorize this formula as a solid, unquestionable block of algebra. Treating it as a monolithic axiom obscures how the mathematics actually function. It is a constructible blueprint. We dismantle this structure into two distinct halves. The blue term, negative b over 2a, maps the parabola's precise center axis. The orange term, the plus or minus square root condition, calculates the exact distance from that center to the x-axis intersections. To understand exactly how this geometric map is built, we have to trace the math back to its source, the algorithm known as completing the square. This equation represents the generalized format of a quadratic function, before any specific numbers are applied. Our first step in finding the roots is isolation. Assuming a is not 0, we divide every term by a to strip the coefficient away from the squared variable. Next, we move the constant term, c over a, to the opposite side of the equal sign. This clears the workspace to construct a perfect square. Now we apply a specific algebraic intervention. We take half of our middle coefficient, which gives us b over 2a, and we square it. We then add this exact value to both sides of the equation. By introducing this specific term, the entire left side of the equation can compress into a perfect binomial square. We then unify the right side. By finding a common denominator of 4a squared, we merge the two separate fractions into a single expression. To isolate x, we take the square root of both sides. This cancels the square on the left and generates a plus or minus condition on the right. Finally, we shift the remaining b over 2a term to the right side. The isolated x is now equal to our highly recognizable quadratic formula. The quadratic formula is mathematically identical to the process of completing the square. It is simply the pre-calculated end state of that exact algorithm. Look closely at the expression trapped underneath the square root symbol, b squared minus 4ac. This cluster of variables is known as the discriminant. It physically dictates the number and the type of real roots the parabola will have. Consider the first condition, where the discriminant is strictly greater than 0. Taking the square root of a positive value yields a real number. The formula will add that real number to our center point and subtract that real number from our center point. This guarantees two physical intersection points on the x-axis. This diagram illustrates how those 2 points behave. If the discriminant is a perfect square, the square root resolves neatly into a rational number, landing exactly on clean fractional or integer coordinates. If it is a non-perfect square, the roots are irrational, landing on infinite, non-repeating decimals. Regardless of whether the coordinates are clean fractions or infinite decimals, a positive discriminant mathematically guarantees that the parabola crosses the real number line exactly twice. Now we test the edge case where the discriminant equals exactly 0, using the equation 9x squared minus 12x plus 4 equals 0. We isolate our coefficients. A is 9, b is negative 12, c is 4, and plug them into the discriminant. Negative 12 squared is 144. 4 times 9 times 4 is also 144. Subtracting them leaves us with 0. Returning to the larger formula, the square root of 0 is 0. Adding and subtracting 0 from our center point yields only one distinct numerical answer. This chart shows the physical reality of a repeated root. Because there is no distance added or subtracted from the center, the parabola's vertex perfectly grazes the x-axis at a single coordinate, refusing to cross over. There is one final scenario to test, using the equation 2x squared plus 16x plus 33 equals 0. Running these coefficients through the discriminant yields 16 squared, which is 256, minus 4 times 2 times 33, which is 264. The result is negative 8. We hit a mathematical roadblock. Taking the square root of a negative number forces the equation out of real numbers and into the complex domain. Graphing this equation shows exactly what complex roots mean physically. The entire parabola is floating completely above the x-axis. It is detached from the real number line, proving visually why no real roots exist. The discriminant functions as an infallible collision detection algorithm. It calculates exactly how a curved polynomial will interact with the flat plane of the x-axis. We can now return to the pre-root stage of completing the square to find the hidden structural center of this math. The isolated constant term dictates the parabola's vertical shift, moving it up or down. The critical structure lies in the squared binomial. Since squares are always positive or zero, the function hits its absolute extreme when this nested term equals 0. Solving the expression x plus b over 2a equals 0 gives us x equals negative b over 2a. Graphing x equals negative b over 2a draws a dashed vertical line through the minimum, perfectly mirroring the parabola. Overlaying the formula, the first half anchors this symmetry axis. The second half, the discriminant, calculates the exact outward distance to strike the x-axis. The quadratic formula is a complete geometric map. The first half establishes the exact structural center, and the second half calculates the precise impact distance.